So, happy Monday, everybody. This is a research talk on picking up on subduction. So, let's see, for those people...
Number 14?
Oh, I assign random numbers to the adventures of the life Tectonic. Okay, so the primer for this was the talk on subduction, okay? And I'll quiz people to make sure they understood the take-home points. And we're going to talk about the recent evolution of Western North America. So to remind us all of the tectonics that were happening, this is the Juan de Fuca Plate and the birth of the San Andreas Fault. And this, when the San Andreas Fault formed, it broke the Farallon Plate into two. And then we have translation of Baja California. And I'm going to run this movie a couple more times to refresh everybody's memory of how Western North America was sort of, put together to first order. This is the key story. There's a few things to look for. One is that there was a continuous subduction zone along here until that triple junction hit the subduction zone, and then we fragmented the Farallon Plate into two plates, with the Juan de Fuca on the other side. And this area here was quite compressed, and it started extending. And here's the time. So it's going to start at 40 million years and progress upwards. And I should mention that this is appropriate for Santa Barbara because Tanya Atwater is a distinguished professor here at UCSB. So we'll start it up again. So here it's one plate, and then now it's bisected. Well, not bisected, but cut in half. And this area here is all scrunched together. So it's about 15 million years. It starts to extend towards the west. And it turns out that this trench here begins retreating. So the overriding plate is Western North America. Another animation to get things kicked off. This is Colorado Plateau, stable continental lithosphere, and this is all fractured. So now time is ticking back this way. And you see the extension here really starts to pick up around 18 or 15 million years. And the Basin Range province here becomes extended. There's a batholith for reference. So this is the major extension here. And that's what we call the Basin and Range. So I got two animations to get everybody keyed into. And you can see that this is Nevada for scale. The Basin and Range is a series of tilted blocks that have fallen as the West has been stretched out. So it's an extended continental lithosphere. It's very weak, and there's high heat flow. And then just to the east of it is a stable Colorado Plateau. And then it's bounded by this other, so people call microplate, the Sierra Batholith. Any questions so far? That's okay. We're all on board.
What's the colors?
Topography. Yeah. So this is, I think, it's a topographic, digital topographic. So I want to go back and tie into the last talk where we left off about those simple generic models that we built a conceptual framework for how plate motions are linked to the width of the subduction zone, right? So no cheating here. Zach, how would a plate subduct if it was very narrow at a small width?
Can you go back?
Now you got to remember.
No, I don't remember.
What are the two options of how the plate can subduct?
Or forward.
Trench retreat. Slab rollback. If it's okay. All right, and if it's really wide, then the plate will advance. A stable subduction zone. So this is a reminder that what you learned before, when the plate is very wide, then most of the subduction velocity is accommodated through plate advance. And when it's very narrow, then you tend to have more slab rollback. So let's apply this question. Sauna. Oh, look what I caught. Typing on it.
I have your slides here.
So what would you expect to happen if you had a wide plate, like the Farallon, that was subducting with forward motion, and then it was chopped in half when the slab window and the San Andreas fault formed? What would happen to this smaller portion?
Starts going back.
Okay, there's going to be a transition, right? So this sort of theory here is going to predict that if a plate was happily subducting forward, Ian, yeah.
How confident would you be in saying that it's suddenly chopped? I mean, it would seem to me to be easy to make the argument that it should be still connected. Right.
It's connected at depth, that's right. So at what point do you call it chopped in half?
That's my question.
You call it chopped in half when the gap between the two slabs is large enough for flow to freely travel through that gap at depth, so that toroidal flow can come around the slab edge, and it's more unimpeded. Okay, good question. Excellent.
Longer range there?
Not really. This is one of the things that's actually sensitive to nonlinear rheology, and our models only have a linear viscosity in the upper mantle, so probably it would be smaller. So I'd say maybe 1,000 kilometers, but probably smaller for nonlinear rheologies. So when you have a plate that is advancing, and it gets cut into two smaller pieces. One of the smaller pieces is going to suddenly, a smaller width is going to start retreating. And so in pictures, okay, here is what North America's sort of margin looked like for about 100 million years, okay? A long, stable, and very wide subducting plate, and lots of, periods of quiescence and compression and mountain building. Okay, so here's mountain building, upper plate in compression, subducting plate advancing.
So does this look like South America?
It does, yes. This is a good analogy for South America.
Those mountains are high?
Could be, yes. Could be a good analogy. Yeah, that talk is recorded from last CIDER. I gave a talk on the Andes last summer. Yeah, exactly. Very, very observant, Kevin. So here, I don't know if people can see, this is 50 million years, and I've sketched in the width of that to a corresponding time period of 52 million years is here. This is the time evolution of the width of Farallon plate. And what we've tried to do here is describe how much, what the subduction motion was of the Farallon plate. Was it advancing, plate advance, or was there trench retreat and slab rollback? So we're trying to estimate from tectonic observables what this partitioning was over time. And you see here it's a maximum. Okay, this is why I've picked this point. It's a maximum because this is where it's its widest extent. And so it's the highest amount of plate motion. Estimates of this scale is for the diamonds, use this scale. And then for centimeters, use this scale. So about 10 centimeters a year at this point for the plate motion. Okay, as opposed to the Juan de Fuca plate, which is more a 1 centimeter a year advance at this point. And you see that at this point we had some, this is the width, so it was about 14,000 kilometers in extent. And then something dramatic happened here. So I just want to point out, here we have shortening observed and orogeny. Okay, the Farallon plate starts to break apart here as this part of the Farallon gets close to the subduction zone. And there's also a slab window forming up on the northern end. And then a little bit of extension starts to happen on the northern end. Yeah?
Oh, hi, Dave. How typical do you think these results would be for a plate like this, given that at the you've got, instead of about 50 or 60 million years, we've got the maximum, there's also, that's the flat slab subduction?
Yes, yes. There is an excellent point. So in our models, so this is a good point to bring up. Our models that we ran, this is observations, okay? And the models that I showed you did not even have an overriding plate. There was no no analogy to Western North America. It was just a free surface. So if you had an overriding plate, you could have these, complications like flat subduction and a laramide. So we unfortunately don't have that. We're not able to address that. The point that I would make is that we had a wide slab, and we had, at the same time, there was compression in the overriding plate. That part we can agree on. And then in the later portion, we have a retreating trench, and we have extension. So other than those we've bracketed the answer in a first order, but to completely definitively show that this is the right, the laramide is a massive complication to the story. It may completely destroy the whole story, but I think we're just trying to show the correlation here where we don't have the overriding plate, that originally it's in compression when it's wide, and then later on it's in extension when it's narrow. So, okay, very good point.
But is the flat slab completely an independent variable, or it's a product of some of these kinematics?
Yeah, it could be that the flat slab may be a consequence of having a very high plate velocity, such that it was traveling fast enough to strongly couple to the overriding plate and then get kind of sucked up under North America. So it's hard to separate the two things. Yeah, I mean that's one of the easier ways to try to generate flat slab subduction is with the squeezing of the narrowing of the mantle wedge. Okay, so I showed you the plate reconstruction and birth of the San Andreas fault. So now, at some point, as Ian said, this gap will get big enough that the plates are going to become kind of acting like two plates, the Farallon and Nazca. And so this is when this dramatic change in plate width occurs. And at a certain point, that gap gets big enough that the Farallon is going to transition from being fast-moving, forward advancing plate to something more driven, subducting more by trench retreat. So you see the change in the partitioning here. And then finally, it's complete. The gap has gotten big enough that transition has occurred. And here we are, around 20 to 15 million years. Okay, this is a key time. That 20 to 15 million years, if I showed you those movies again, you'll notice the basin and range really doesn't start taking off until around 15 million years ago. Okay, and so this is the width of the Farallon plate. It's quite narrow at that point, and it would tend to favor faster trench retreat rates. So it's very correlated to the birth of the basin and range. And then now, here it is, present day. It's really small, and we still have active extension in the northern part of the basin and range. So there we are. Okay.
Borne out by genetics that the extension is primarily north?
I mean, there's still active. I think this is where the concentrated extension is. But this is. It depends how long you average over. So geodetics only give you an average for right now. You need to use other observations to get a longer average. All right.
Do you
Yeah.
expect the progressive younging of the subducting plate to be at all important in the story?
It could be. I don't think it's going to compete with what we're presenting, the first order thing, and I think that would probably come into play at some level. I mean, certainly if you're subducting younger material, you have more deformable edges, so it'll help open that gap up faster.
I have a question. On the plate reconstructions back before the highest velocity peak, are those pretty robust?
There is pretty good magnetic anomalies to produce that to first order. There's a lot of second order complications of the microplates that develop in the area, especially like the California borderlands. So these mountains just off the coast here, those islands are part of this California borderland transverse ranges that rotated out. So there's a lot of large complications, but on that regional tectonic scale, that's first order accurate.
I think for the subduction of the Farallon plate, there was an old paper by Peter Berg, which talks about the shallow subduction and then the delamination from outer side to inner side will be consistent with the volcanism in this region.
Yeah. Yep.
So, is that the same observations?
It's using similar observations. This is probably the best, synthesis of data tying the extension of the basin range to these observations. But what this provides, what these models provide, is an underlying physical mechanism for what created extension. So it's because in that he's invoking a subducting plate, and what we're doing is giving the dynamics of the subducting plate and why it would be behaving the way that it does. Yeah. So with Farallon, I just showed you the Farallon plate is subducting off the coast, and you can see at 900 and 1100 kilometers, there it is, right? So this is the Farallon plate that used to be off the coast 50 million years ago, when everything was nice and simple. Nice, long, wide subduction zone, and you see it down there, nice sheet. This is kind of broad, right? This is not a narrow feature, but it stands up pretty well. And when you use plate reconstructions going back from 80 or 100 million years, and you apply this as a surface boundary condition on a mantle convection model, you inject the cold downwelling to be where the paleo subduction zone was, and these convection models did exactly that. And at these depths, they agree pretty well. It says, well, this blue stuff here is very likely what the Farallon slab was 80 to 50 million years ago. Nice linear sheet. Looks just like a subducted slab. It's good. We got EarthScope online and started getting very high resolution tomographic images of the upper mantle. Here's 100 and 250. Well, we see the Juan de Fuca up there. That's good. Looks like a nice linear sheet, just looks like a slab. And okay, you see it. These are two different models. I'll show a combination of pictures from 4 different models. But it starts to break up. There's a hole there, and it's a gap between these two north and south parts there. So, and where's the rest of it? I guess it's only about that extent for this age. And then let's look lower down at the bottom of the upper mantle, 500, 580. It's not looking like a sheet anymore. It's not recognizable like the slab that we saw. In fact, these things were argued maybe they were just lithospheric drips, and these little blue blobs everywhere are. That doesn't look anything like what a subducted slab should look like. So what happened to it? Where did it go? All right, just to drill the point home, there used to be a subducting slab off the coast, and when we look down at this depth using 3 different tomography models, we see a bizarre mixture of cold anomalies scattered around. So it's okay deeper down, it's okay higher up. Something happened in between.
Is it Yellowstone Plume?
Oh, Yellowstone. So what we can do is repeat that experiment that was performed before, but now in 2008, a very nice compilation of the age of oceanic seafloor and very sort of higher resolution reconstructions, about a million years, and then also the paleo age grid. So this is a higher resolution surface boundary condition that could be utilized. And so this is the first part of the data assimilation model that this is work I'm showing Lijun Liu at Scripps and I worked on. So this is the top view. So this is North America. We don't have an overriding plate here. It's just a free upper boundary. And this is our Juan de Fuca plate. We have weak plate boundaries, This is the viscosity. So a high viscosity Colorado Plateau. There's a higher viscosity North America, and a broad, weak region sort of representing what the basin range is. And this viscosity contrasts across the plate boundaries. So you have to have weak plate boundaries, or the plate tectonic system locks up because diffusion, you have two cold things, and they'll diffuse and kill off the plate boundaries. There's a big, very low viscosity mantle wedge in this. This is our model set up in cross section. You see, here's the mid-ocean ridge. Here is a slab perturbation, and this model begins at 40 million years ago. So this is exactly the time when subduction kind of gets reestablished off the coast of North America. Now, importantly, this is the plate. Its thickness depends on that paleo seafloor, the paleo age grid that was the model input. Okay, and there is no large-scale circulation in the mantle. The box depth is, I think, 1,000 kilometers deep. I'll have to double check on that. But essentially, it's a big warm bath. It's an isothermal bath. So this plate that we've defined is just going to sink into a warm bath. There's no large-scale overturning motions to drive plate motions. This slab, the only thing that's driving it is gravity from its own negative buoyancy. So it's just going to sink into this inert warm bath that will react with its down. It's similar to the models that I showed, okay? Except this time there's the energy equation is being neglected. Okay, so there's a few other technical things that I could go into that make this model successful, but I don't want to bore you. So we're going to look at the evolution of this in cross section, going from 35 to 0. And here's the location of the trench. And so it's sort of marked with where the original location was and where the current location is. So at any point, this distance here tells you the amount of extension in the overriding plate. And you see this amount of extension, it's cumulative, but it really starts to increase right around 15 million years. So at 10 million years, there's a good amount of extension, and this is just recorded in the plate motions. And so the trick here was to self-consistently get the internal dynamics so that the slab would fall away from the surface at the same rate that the plate kinematic boundary condition was telling it to. And so it's hard to get these things actually synchronized. But when you do, you notice that right around 20 million years, at 15, look, there's a big gap here. It kind of broke apart. And then this part here starts to sink down separately away, and a new segment forms. And it also kind of starts to segment a little bit. So it's actually sort of 3 segments here. And so we've drawn in green what these 3 segments at depth are. Okay.
Questions.
Yeah.
Why the background mantle is isothermal? The temperature is the same.
Yeah, because why is it isothermal? Yeah, so this is it's isothermal because we are trying to demonstrate that the subducted slab itself is the only source of buoyancy that you need to produce thermal anomalies that are in the right location of where the observed seismically fast anomalies are. So these are just sinking under their own sinking trajectories defined by only what's in this model. There's no effect or influence of a large-scale flow. The large-scale flow isn't shifting these around. And it's a representative temperature for the upper mantle. It's just saying the upper mantle is basically a big warm bath that the plates subduct into. So so the point is, we see this here. This is exactly the same time that the extension starts to increase, because at the surface, this is the time where the plate width shrunk.
So is this a full 3D model?
This is a fully 3D spherical regional model. So this is coincident. This little break here is coincident with that change in the width of the Farallon plate. Yeah.
Where's the slice relative to where the triple junction hit?
North. This is at 41 degrees north, so it's a bit north of that. Okay. So this took a lot of models. I'm showing you the best model. But there was a lot of models, and Li Jun made a lot of models. And this guy here, we've drawn a representative sort of crude representation in green here, where that little broken slab fragment is. And both the depth of where it is, the translation of where it is across can change depending on the model. Its vertical position can change depending on the radial viscosity profile that you pick. Its shape can change depending on the strength of the slab that you've chosen. So all of the features of the shape and location of this are highly sensitive to the model conditions. It turns out that green thing there matches up very nicely with these 4 models of tomography that all seem to indicate there's about 3 segments. This one shows 3 segments in isocontours of the VP. I think that's probably the VS model, Schmann. This is probably, I think, the VP. And they all show that there's definitely, all of them have a gap at that depth. This gap is in a few models and not in these other 2. So that's kind of reasonable agreement with this model.
What temperature is white?
It's not a temperature, it's a seismic. Oh, white? Oh, I don't remember what white is. So yeah. There, Rohan?
So you said before you say these are segmented when you have flow in between these 2 parts.
Yeah.
To each segment. On the right one, the bottom right one, you can see that there's flow going through. But on this top left one, can you model like flow through, or say that it's differently segmented, or it's just kind of thinned out, or? I mean, because if your tomographic or models are showing 3 distinct segments, does it show that it will form a segment, or is it kind of like putty and stretching?
It could be just stretching. Yeah, I mean, it's not clear if it's discontinuous. It could just be deformed, but there's a little kink in there. Okay, maybe it's not separated. Yeah.
How did you treat viscosity? I missed that.
So we have lots of different viscosities. So we've tuned, and this model is a forward model, so we've varied lots of different types of viscosity. One is the radial viscosity contrast across the mantle. One is the relative strength of the viscosity of the slab relative to that background, and then viscosity is up here in the at the surface for the mantle wedge, how weak that needs to be. So there is a temperature dependence in the cold part, and then the other important thing is the viscosity in the subducting hinge, and that plays a critical role. So there's lots of things that you have to get exactly right to have this outcome of these sinking trajectories and shapes of these actually be perfectly in line with the tomography. Okay, so the point is we can actually do this without needing a large-scale circulation. This is just locally what's happening with the Farallon sinking under gravity as it subducts, according to where the plate was from plate reconstructions. Now let's look a little bit in map view. So in map view we've got there's actually 3 segments, and we're going down this is in time coming across at 100 and 500 kilometers. So actually this is the shallow in the earlier part, and then it's sort of these same features laid deeper. Okay, so we're trying to track these features over time and depth. So we're trying to, as this sinks, some time elapses, and then it's a little bit deeper. And you can see the evolution of this relatively straight fragment becoming curled because there's flow coming through there and deforming it. And it ends up like a horseshoe kind of shape. So it actually, as it sinks through the upper mantle, it begins getting deformed, and this one as well is getting deformed. And so at 500 kilometers, you see there's 2 separate kind of circular blobs that have been folded around. All right. I'll skip over. This is the evolution of the hole up there at the front. There's segmentation to the north, and so this is our forward model. Okay, of this is our forward model, our best fit. You see this horseshoe shape, and you actually see that horseshoe shape in a couple tomography models. In this one, you see this horseshoe shape that's the most prominent of that horseshoe shape. So this is like a good indication that maybe it's not a lithospheric drip from the continent. It's actually just the Farallon slab. All right.
You also see it in SKS plate.
Yes, I have another part of this talk I took out for the flow.
You see
All right.
flow around and no one is out to be.
So we've covered the basin and range, the tectonic signal. We've covered the tomographic signal. And now we're going to cover the volcanic signal. All right? So the volcanic signal in western U.S., so these ages are in times. And the acronyms here I'll go through. Here's Yellowstone for reference. You can see the map of the U.S., present-day location of the Juan de Fuca Plate. And this here, you may know, is the Snake River Plain, the eastern Snake River Plain that leads to Yellowstone. This here shows a sort of tectonic parabola that demonstrates a topographic swell, similar to like we observe in Hawaii, which is inferred as a mantle plume. So it's perfectly reasonable to say, look, there's a hot spot track. Look, there's a plume. There's a topographic swell. Looks like a plume. Okay, gets harder because for some reason this hot spot track takes a strong turn here. And if you track it back to its origin, it's up here in Oregon, the Columbia River basalt. And the first location of the eruption is at Steens Mountain, which I'll show on the next slide. So we call it the Steens Columbia River basalt. There's this other bizarre part of the story where there's Younging volcanism in the opposite direction, towards Newberry. But this is the high lava plains. It's a felsic volcanism, not basaltic. And it's getting younger in the opposite direction. So this is the northern Nevada Rift, which happened at around the same time as Columbia River basalt. The Columbia River basalt is essentially north-south. If you see, it's orthogonal to, here's the direction of plate motion. This follows the recent hotspot, or eastern Snake River plains, while the high lava plains seems to be orthogonal. And the trend of the volcanism for the original flood basalt seems to be opposite both of those directions. Okay, so this is a massive flood basalt, and it's generally been attributed to the arrival of a mantle plume. And a plume head comes up at the surface, it melts, it creates flood basalt. Somehow this plume conduit gets twisted around and then it starts to behave normally. Now it's at Yellowstone.
Okay, Lava Beds National Monument is just off that, right? Just south of your HLPs?
Could be.
In California. And then you get Mount Lassen.
Okay, Mount Lassen.
Is connected entirely?
Mount Lassen is related to this guy here. That's arc volcanism. Yeah, Mount Lassen is the very bottom of that. If you just track this across over here, that's Lassen.
But it's purely accidental that I'm getting those HLPs just to the north of Mount Lassen?
The HLPs are distinct volcanism from the arc. The arc is all along here. You've got all the...
But you do have Newberry, and you also have Medicine Lake, right, which are within sight of the arc volcano.
Yes, that is actually heading towards the arc. So people propose that this is arc volcanism. Absolutely. This is somehow related to flow coming, maybe around. Is this the back arc basin? So this is volcanism in the back arc basin, but except that it's not in the back arc because the arc is actually back arc. It's behind the back arc. I just wanted to show you that these trends don't line up at all. So this is the trend of the flood basalt. It's a linear trend. It's not a large sort of, round shape. So to look at the pattern of volcanism in more detail, Okay, these are the dike swarms that have drawn in. And this is the progression. This is the first spot of volcanism. It steams dikes. And it starts to propagate towards the north afterwards and propagate south along the northern Nevada Rift Zone. And then superimposed here, so this is this region with the little dike swarms. And here's the high lava plains progressing that way, Snake River Plain this way. So it's a large area. It actually started here, though. It actually started the sort of origin of it. Let's see, where's Steen's? Probably that guy there. So maybe this here, but then the eruptions, the larger eruptions were focused up here, the Chief Joseph dike swarms, and these were the units here, the Imnaha and Grand Ronde. Okay, so this has been a very perplexing issue with fitting it into the paradigm of a plume head flood basalt. And you can even see here the volcanostratigraphy. There's the first eruption at the bottom, the Steens. And then it comes up to the north. And then you get the really big unit, the Grand Ronde, which is the most voluminous. And it has several sequences. These are different polarities. In magnetic reversals, actually, there's a nice little reversal happening right during the sequence, which is kind of rare. Oh, look at the ages, 16.6 to 15 million years, right around that same magical time that transition was happening of a wide slab, a wide plate to a narrow plate. So, as I said, this is a long-standing enigma for people trying to understand this volcanic pattern. There's been a lot of things proposed, going back to Pierce and Jason Morgan. So plume head, obviously. You see Morgan, you can close your eyes and think there's going to be a plume there. There's another sort of conceptual model of plumes breaking through. This is a little revision on that the plume can somehow break the slab. I guess we should start up here, okay? And it starts to buckle and break the slab apart. Then you have the plume. Okay, it's reestablished now. There it is, feeding Yellowstone. And the other thing is that maybe the whole thing is the high lava plains is a back arc process. So Rick Carlson has that. This is a model where the plume head actually comes and disturbs some of the mantle lithosphere and weakens it to make that mantle lithosphere drop away and then create flood basalt. So everything has been proposed essentially. And this is an old, I apologize for the age of this. It's a 2005, so it's pre-Earth scope. So I think there's a lot more, better images of like a putative Yellowstone plume. However, this one's nice because it actually shows the deflection at the 410 of something that you would expect if you had something warm going through the 410. Okay, well, we want to look back at that rupture, and I'm going to zoom in here. Here's the ages. So before I showed a 5 million year snapshot. So we'll zoom in at that period between 20 and 15, and we'll watch this hinge and the retreating trench. And it does look like there's this systematic, this is a zoom in of that area of interest here. And for reference, a dotted line shows where the slab used to be. And so you have this thermal erosion happening. And that's kind of interesting. So this is really how, as soon as this plate transitions due to its width, it starts to stall and at the surface. And this actually kind of conspires to drive flow and erode the subduction hinge itself. That's not under review anymore. Sorry, that was published in February. Okay, whoops. There it is. Okay, that's at the right reference. And so if we started to look at the three-dimensional structure of this slab, we notice, okay, for this isocontour, we've got this little slab here, and these arrows popping through show the velocity of the upwelling underneath it. So if this is a coherent sheet, it's indicative of a high velocity underneath it. And this is the 16 million year where this tear occurs in the subduction hinge. And so this is the first tear. And we project this tear onto a map of the US. And this is the size of the tear. It's the pink stuff. And here's the trace of the subduction zone. That would be just this part here. So this is the deeper part of the slab. This is the Juan de Fuca plate. And this is the subduction hinge along here. And then this is the Pacific plate speeding away. It's kind of an awkward view. But if we map that hole to the surface at this tear observed in the model at 17 million years, and it is spot on where the first eruptions of the Steens Mountains were. So this is an amazing coincidence. We've used a geographically referenced model to just tell the slab where it was in space and time, and it came back and said, I've got a hole here at 17 million years, and that hole just happens to be where the Steens Mountain. Well, let's watch how this tear in the slab evolves. Well, it propagates to the north and to the south at the same time, and there's the extent of that tear at 15, or sorry, I think this is 16 million years. I didn't have a 17. Okay, it's beginning to have sort of this north-south trend, and this advective flow is driven by pressure rearrangement. So this tear, it's just basically propagating to the north and south, and then it really starts to open up. It happens to open up quite an extent at 15 million years, coincident with the northern Nevada Rift. And it's actually got quite a larger area to the north at 16, which is around the time this Grand Ronde sequence starts to erupt. Chief Joseph Dikes forms. So these are the major dikes here. And now the blue, if you can see that, it's essentially this massive opening between the bottom part of the slab and the top. And the velocities start to die down a bit here, but at 14 million years, this is starting to equilibrate and die down. So the flow is going to start dying down. The rupture is equilibrated. Now we've gone to 10 million years. And so here's the extent of the final volume. So this is a map projection of the sequence of tears that happen. And we estimate how much advective flow could come out through this hole. And if it's hot enough, it could remelt the basaltic crust. And remelting the basaltic crust is another part of the story that is a nice agreement with the geochemistry of one of the units there. It actually looks like remelted crust. So this is our story for how this was in place. It's actually it's completely a product of mantle flow tearing a slab and producing a flood basalt. There's no plume head anywhere. But if you took away the plume head, what happened to the Yellowstone plume? It's still there. I told you that I thought there was a plume there. So now I'm going to... Okay, were there any questions here? I'll just go back.
Was the tear because of slab rollback?
Yes. The plate is transitioning from forward motion. So we're just applying our sort of conceptual model of how plates work. We observe that the plate comes to a critical width where it wants to transition from forward plate motion to trench retreat, which happens to be at this time. And during that sort of period where the slab is stalled, a tear develops.
So do you see the offset?
Yeah, this offset here. I mean, this is just a representative isocontour to show it. I think the major thing to remember here is that there's no plumes in here. There's just a warm bath, isothermal bath underneath. And we still can generate volcanism without a plume. There's no large-scale flow, but we have constrained this model because this is our best fit model to the seismic tomography. And then we just interrogated it a little bit more, but it is driven by plate reconstruction, so it's because that's its boundary condition, and other things we did. It's consistent with plate reconstructions and the formation of the basin and range, and then some aspects of geochemistry. So
you assuming anything surprising about the slab rheology?
It's weak. Slab is weak. That's why these things deform so easily at depth.
And is this because this subducting slab here is actually unusually hot to begin with?
Oh, I think a lot of the slabs are just a lot weaker than what people have been reporting them to be. In our models, we've had pretty weak slabs for a long time, and this is kind of vindication that you get a lot better agreement with seismic tomography, and even a predictive capability of, if this is the origin of the flood basalt. It's the slabs are very weak. I mean,
You predict the seismic anomalies?
We have not done any kind of synthetic seismic processing of the geodynamic models. Yeah, but I mean that's kind of probably a tunable thing as well. Yeah.
The temperature are the temperature gradients a little bit flexible, or do those come from the viscosities of the slab that you choose? Like the eventual temperature gradient.
So it's just thermal diffusion. I mean, we're specifying a thermal boundary layer of the appropriate age based on the paleo age grid, and letting that fall into a warm bath, and then it's just thermal diffusion, diffusing those anomalies away, diffusing that thermal boundary layer as it sinks.
And this location of breakthrough came out of your best model?
The best fit model to the seismic tomography.
Does the place where the tear started reflect sort of the wavelength of this?
It turns out to be about the central part of that Farallon plate, and very good insight. So where would you expect the pressure to be concentrated if you opened up a gap on one side? You had toroidal flow on both that gets concentrated at the center, and so there's this. That's why it actually starts at the center. I'll go back. Nice work, Ian. So this is the extent, and the tear happens in the middle where the pressure is highest. Yeah.
How old is the plate when it gets subducted?
The plate at this age here, I don't want to make a guess. It's young. It's like 30 or 40 years.
So it's if you were to account for like the composition of the lithosphere, it might be actually a little bit thicker than you know.
Yeah, I mean, let's see. We could compare that. I forget what this paleo age grid is. Do I have North America here? I think it's the beginning. It's normal, sort of. That's 100 kilometers there, right? Yeah. And then the lower part's always weaker because you have thermally activated creep there. So let's go forward. Let's a little teaser on the. So if the Steens Columbia River flood basalt wasn't a plume head, but we still think there's a Yellowstone plume, how can we reconcile this? Okay. And so these are some models that Kelsey Druken, who is now postdoc at Carnegie, has been working on with me. I should full screen that again. And those cartoons where the plume was coming and pushing up the slab and ripping it apart, right, and creating a hole in the slab. The plume was pushing through the slab. Okay, well this is a direct test of that. Okay, for reasonable assumptions of plumes and slabs. So there's our plate, similar to those free subduction movies that I showed. And here's the plume. It's popping through a higher viscosity lower mantle. It's draining a layer of a buoyant material under there. And we tried a bunch of different initial plume locations. So this plume is going to rise up. This plate is going to sink. The plate is going to induce a toroidal flow, circular, and this plume is going to interact with the subducting plate. Okay, and I'll just show you a couple representative models. Here's our little mushroom cap. It's initially starting under the plume. It's rising up, sort of engulfing the plume. Now the trench is retreating into that. The original plume material is yellow. The conduit material is red. And the thing is, it's dragging. This plate is actually dragging a lot of plume material down with it. And it didn't really care. It didn't break up. The plume was right underneath it, and it didn't care at all. It didn't break up because there was a plume there. It just kept subducting, and the plume material, because it's weaker, just gets sucked around into the mantle wedge. So this is a view from behind. You can see the conduit material and the entrained plume head material. Just the plume head gets sheared off. You can see the nice little conduit here. It's very highly deflected because of the flow from that toroidal flow. This is a front-on view looking at it. You can see that plume conduit starts from behind the slab and kind of does a corkscrew maneuver to the front of the mantle wedge. And that plume material is ponded. So, one more. Okay, in this case it starts in the front and it rises a little bit faster. It goes straight into the mantle wedge and it starts to get entrained down into the mantle wedge. So in this case, there's a surprising amount of entrainment down, and this plume material, even though it started off quite far away, it's still able to get fed into the back arc for a long period and from a long distance away. So this one might be more appropriate to Samoa and interacting with the Tonga Trench, a significant distance away. So I have like 30, Kelsey has run about 30 of these experiments, and each movie is distinct and interesting. We'll try to summarize them, and that's a time scale for how fast the plume rises compared to how fast the plate is rolling back. So there's an interaction time scale we've named tau star. And these experiments here show two different angles of the same. Everything else is the same location, same slab, but the plume is slightly different in each case and has this has the longest interaction time. Sorry. This is where the time scale of plume rise and subduction is comparable. In this case, it rises up very fast. In this case, it's rising up very slow compared to the plate retreating. So we've sort of done an array of different experiments that can sort of see the time evolution of these. And some of these look sort of like cobras dancing, like the slab is a snake charmer, and the plume is rising up from behind the slab, but it kind of snakes around and goes into the back arc basin, and we can then do sort of a regime diagram of how plumes behave if they're based on their initial position for a given buoyancy and interaction time. And so this is interesting because it shows you that plumes can, if they're strongly controlled by the dynamics of the subducting plate. They're the passengers that are getting moved around, not the other way around. So I think that's all I had.
Do you need the plume? Could you create everything, including Yellowstone, without it?
I can't make Yellowstone. Subduction can make flood basalt, and
it can make the high lava.
Maybe it can make the high lava plains. This argument's gonna.
But you can't make the Snake River Plain.
I can't make the Snake River Plain. We can't make a topographic swell. Yeah. But the thing is, you can envision a very a different history from a plume just sort of having a vertical life. It's spending its life in a vertical plume. These plume conduits can be highly deflected, and so that kind of gives us hope that we can piece together once that gap, the Farallon tear, gets big enough, the take-home message is the Farallon would have highly disturbed and maybe even killed off the Yellowstone plume for some amount of time because the conduit is so weak in comparison. But once that gap opens up and the buoyancy source is still underneath, it can reestablish the plume conduit and happily sort of track back from the East Snake River plains to present-day location. But that means that possibly and this has been proposed, that the Yellowstone plume is much older than the Colorado flood basalt, Columbia River flood basalt. And it may have been going back to 40, 50 million years. And
there's all these basalts
on
the Oregon coast.
Bob Duncan is exactly. Rob Duncan? Bob Duncan? Robert A. Duncan has proposed that exact scenario, that coast ranges on the Oregon coast are an accreted oceanic hotspot track and ocean island basalts. So the Yellowstone plume may have had a former life that was strongly interrupted by the Farallon plates sort of, midlife crisis, transitioning from a forward-moving plate to a retreating trait and retreating slab, and highly destroying all of the plume conduit that was established at the time. Zach?
So did anyone model a plume successfully going through a slab, or how much detail did those older papers describe?
Those were cartoons.
Those were just cartoons.
Yeah. Yeah, the other thing is that it's really, the reason those cartoons lasted so long is because people really think in terms of vertical cross-sections and not three-dimensional phenomena. Like the toroidal flow is inherently from the three-dimensional geometry. And it doesn't exist in 2D models. So, the intuition that you can apply when you draw cartoons is a derivative of, the geometry that you're used to thinking of.
Did you tried this, like putting really, really large thermal anomaly in the plume, but really almost no temperature dependence of viscosity or something, like explosive.
A stiff plume, a stiff hot
like a rocket that shoots up through the slab. There's got to be a way.
I guess I would let someone else do that.
Okay.
Yeah, we didn't do that. Yeah.
Can you estimate from Lejeune's models the amount of volcanism, the volume of volcanism?
We did estimate, but we think it comes down to chemistry, and you have to know what you're doing is kind of thermally eroding the oceanic lithosphere, the depleted portion, and you're thermally eroding however much oceanic lithosphere you have until you get to the crust. Once you get to the oceanic crust, if temperatures are high enough, you can remelt that crust very quickly. So it's kind of a pulse of volcanism. That's more controlled by the area of crust that's getting exposed to the warmer temperatures.
And alternatively, the plume might be shut up by the subduction zone sitting there, and once the gap opens, with that additional plume.
Yes. Yeah. Well. Hopefully, we're going that direction. The idea is to take those models of Lejeune had, and take these are preliminary. We're trying to build a general, a generic sense, a conceptual framework for how plumes and slabs interact, and then combine them together to try to understand the whole history of Yellowstone with a plume. Repeat that process. But we need to have this foundation laid in the general sense how these things interact before we do like very detailed data assimilation, very expensive models.
So you would say that the plume contributes to the movement of the step tear that controls where it occurs?
That would be fair to say. This talk's over and the wine is out.